Hey guys, so welcome to the session on encryption and coin flipping. We have three talks. The first one is on quantum encryption with certified deletion. It's going to be given by Anne Broadbent. So Anne, I'll pass the floor to you.
Okay, hi everybody. This talk is on quantum encryption with certified deletion, and it's based on joint work with Rabib Islam. So I want to start with a physical analogy to the scenario that we're going to be looking at today. We consider Alice places a message into a safe and locks that with a combination and sends the safe to Bob. At that point, Bob has an option. He could choose to return the safe as it is in this closed state to Alice, in which case Alice would be convinced that Bob did not open the safe and to read the message. Or he could keep the safe, and when the combination is revealed, open and read the contents. And this is actually an exclusive OR. In the physical world, he could do one or the other, but not both. And here, when I talk about the combination being revealed, Alice could simply broadcast it. So the question is, could we achieve this type of functionality in the digital world? And the answer is a resounding no, at least if you're looking at encodings using classical information. So here's a simple proof by contradiction. Say Alice encodes a message using a key K and sends that to Bob. Then Bob can make two perfect copies. With the first copy, he could convince Alice that he did not read the message. And with the second copy, he will wait to receive the combination and open and decrypt. So what we're going to do today is we're going to show how quantum mechanics enables the best of these physical and digital worlds. Namely, we'll give an encoding for a classical message into a quantum state such that Bob will be able to prove that he deleted the message by sending Alice a classical string. And this is what we call quantum encryption with certified deletion. There's some related work here that I unfortunately don't have the time to go into details right now. I wanted to give you an idea of the scheme via an example. So here we're going to be encrypting a message of 2 bits. And in order to do that, we sample first theta, which is 4 random bits. We sample R, which is also 4 random bits. And then we create the Wiesner encoding, which is the string R in basis theta. So when the theta is 0, we encode the bit R in the computational basis. And when the bit theta is 1, we encode R in the diagonal basis. Sorry about that. Okay. And then let R comp be the substring of R, where the qubits are encoded in the computational basis, and R diag be the substring of R, where the qubits are encoded in the diagonal basis. The encryption of M will therefore be the Wiesner states together with M XOR R comp. So from here, if Bob wanted to delete the message, he would simply measure all qubits in the R sub theta in the diagonal basis. And this would give him a string, if he's honest, with 2 wildcards. These would actually be uniformly random bits, and two deterministic bits, namely the substring R diag. In order to verify deletion, Alice would simply check that when theta is equal to 1, the positions of this string are consistent with R diag. To decrypt using a key theta, Bob would simply measure all the qubits in R theta and only look at the substring R comp. And then using the value of R comp, he can, as well as the classical part of the ciphertext here, he could deduce M. The proof intuition is, well, one that is present in a lot of quantum cryptography. So basically, as the probability of predicting this diagonal basis string increases, that means that the adversary is good at producing a proof of deletion. The probability of predicting the R comp bit string decreases. So that means that the adversary becomes unable to decrypt even given the key. So another way to think about this is that if Bob wants to be really good at convincing Alice that he deleted, he should really measure all the qubits in the diagonal basis. But measuring a qubit that was initially encoded in the computational basis, in the diagonal basis, will effectively erase that part of the information. So this entropic uncertainty relation is underlying here the intuition. This is the entropy, and C is the maximal overlap of the observables. Here's how we define the security of our scheme directly applied to the scheme that we're looking at. So we consider Bob to be adversarial, and he chooses a message, sends that message to Alice. Alice chooses a key as well as a random bit B. Based on B, Alice will either encrypt the 0 message or the message that Bob sent, and she sends that back to Bob. Bob then produces Y, which is the candidate proof of deletion that Alice verifies using the key, and that makes her accept or reject. Then Bob is given the key, theta, and then produces a bit B prime. And then he'll win the game if and only if the bit B prime is equal to the initial bit B. That is, he was able to gain information about the message. And we'll say that the scheme has certified deletion property if this probability of winning is close to 1/2. Just a quick outline of the proof. We will first consider the entanglement-based game, and then we'll apply some entropic uncertainty relations that have been initially developed in the context of quantum key distribution. There are refinements of this basic protocol. Namely, we'll do a noise-tolerant protocol by using error correcting codes. And we'll also reduce and make uniform the advantage that the adversary has here by using privacy amplification. So we give an upper bound on the max entropy. This gives us a lower bound on the min entropy. And then we're able to give the full security of this protocol. So in summary, we have a classical proof of deletion. It's prepare and measure because we're sending and measuring single qubits, and we have noise tolerance. Thanks a lot.
Great, thank you so much for your talk, Anne. The next speaker is Wei. He's going to be talking about on security notions for encryption in a quantum world. So the floor is yours, Wei. Feel free to share your screen.
Okay, sorry. So hi everyone. So today I'm talking about our paper on security notion for encryption in a quantum world. This is joint work with Céline Chevalier and SNL Primary. So usually when we talk about standard security or even post-quantum security, we assume that the adversary are either classical or quantum, but he only has classical communication to the honest party or classical access to the primitives. So we can go one step further when we can consider fully quantum security, in which the adversary not only have quantum computers, but also have quantum access to the primitives or the honest parties. So this motivated by scenarios such as running classically obfuscated programs in quantum computers. So in our paper, we focus on studying fully quantum security for classical encryption. So previously, this lab work was started by Bonnet-Zandri in 2013, in which they give the first security definition for quantum security, which allows quantum learning queries, but only classical challenge query for both public key and submit key with chosen ciphertext security. And in 2016, Gagliardini, Hunsing, and Strapner give another security definition, which allow quantum challenge queries, but they are restricted to a special minimum oracle. So basically, the minimum oracle has only one register for both input and output, while usually in this standard oracle model, we have two different registers, one for input and the other for the output. And also the definition limited to symmetric key encryption with chosen plain text security. So the open question is to define security notion which allows quantum chance query in the standard Oracle model, both for public key and symmetric key encryption with a CCA security. So in the classical setting, the security is modeled by a game between the adversary and the challenger. And in the CCA security, the challenger needs to be able to recall the chance query from the adversary so he can prevent trivial attacks. But when we translate this notion to the quantum setting, it's difficult because the no cloning theorem. So now the chance could be some quantum state, so you cannot easily copy that. Or it's also because the measurement is shortness. And another reason is that because in a paper by Bonnet and Zandri, they give the impossibility for any left or right distinguishability notion. So basically that in this kind of notion, the adversary can send out two messages, M0 and M1 as a challenge, and the challenger will encrypt one of the two messages. And so any quantum translation of this notion will be impossible to achieve. So in our paper, we answer this open question by giving us first achievable and meaningful chosen ciphertext security definition for public key and symmetric key in the quantum setting. So let me give you a brief overview of our technique. So first, to bypass Bonnet-Zandri impossibility, we switch from a left or right indistinguishability notion to a real or random indistinguishability notion. So this real or random indistinguishability notion has been studied before by Masazebi and Straff in 2016. And very recently by one of our authors, they saw that actually real or random indistinguishability notion is one of the strongest one we could achieve for encryption in the quantum setting. And to define chosen ciphertext security, we adapt a Zandri compressed oracle technique to randomized functions. So now you can consider the encryption as a randomized function. So using the recording technique, we can record the chance query, and then we can define the quantum notion for encryption similarly to the classical setting. So in our paper, we also give other results. So we saw that encrypted mechanism shows CCA secure, similar to the classical setting. We give a compiler to convert any Bonnet-Zandri secure public key encryption scheme to our stronger security definition. And we also give the first definition for non-malleability in the quantum setting for classical public key encryption. That's all. Thank you.
Great. Thank you very much, Ray, for your talk.
Thank you.
Okay, and let's move on to the third speaker in the session. That's going to be Atul Singh Arora. The topic is analytic quantum weak coin flipping protocols with arbitrarily small bias. So Atul, feel free to share your screen and start whenever you like.
Okay, thank you. I suppose everything is in order, so I'll start. Okay, hi, my name is Atul. As already mentioned, I'm excited to present our work on weak coin flipping. This was done jointly with Jeremy Roland and Chrysula Vlahu. Right, so the coin flipping problem is the following. So there's Alice and Bob who wish to agree on a random bit by exchanging messages. And they don't trust each other and they want to arrive at a random bit at the end of it. So a variant of this problem is called weak coin flipping, where Alice wants a heads and Bob wants a tails. So this is known. In distrustful cryptography, it is the strongest known primitive, which can be done quantumly with information theoretic security, while classically it is impossible without further assumptions. And I should say that weak coin flipping is contrasted with the former, and the former is called strong coin flipping. So a coin flipping protocol is essentially any scheme of sending and receiving messages that solves the weak coin flipping problem. And obviously not all protocols are going to have the same security. The relevant figure of merit here is called the bias of a protocol, and it's denoted by epsilon, and it varies from 0 to a half. A 0 corresponds to a perfectly secure protocol, and a half means that the protocol is completely compromised. Okay, so perfect strong coin flipping was shown to be impossible by Kitaev, who showed that there's a lower bound on epsilon. Moshe, in his breakthrough result from 2007, showed that weak coin flipping protocols with vanishing bias actually do exist, but his proof was non-constructive. The best known explicit protocol until recently had a bias of 1/6. Last year, it was improved to 1/10. And in that same work, a numerical algorithm was proposed that approached zero bias. This left the status of weak coin flipping in a limbo. Is it solved? Is it not solved? And in this work, we sort of remedy this problem, and we give the first analytic solution to quantum weak coin flipping. All right. In this study, 3 equivalent frameworks were introduced by Kitaev and Moshon. The first uses SDP duality to certify the bias of coin flipping protocols. The second is called the time-dependent point game formalism. Here, one starts with 2 points, as shown in the graph, and these points are moved in successive frames by following certain rules, which are easy to state. The coordinates of the final point encodes the bias of the protocol. Finally, there's the time-independent point game formalism, and this is essentially a simplification of the point game formalism itself. It was in this formalism that Moshon proved his fundamental result, that is, weak coin flipping with arbitrarily small bias is actually possible. And this we can see by setting K to be arbitrarily large. So while these formalisms are known to be equivalent, the last step is non-constructive. Recently, in 2019, it was shown that numerically one can convert point games into explicit protocols, but no analytic solution is known. In this work, we give an analytic construction for converting Moshon's point games into explicit protocols. And this step can be understood as follows. So suppose we are given a point game and we focus on 2 frames of this point game, as denoted in the graph. This corresponds to applying some standard unitary, which is written in black, which is written in gray, and a non-trivial unitary, which is in black. This unitary is essentially specified if we can find the unitary that I have written in the blue box. So here, the unitary U has to satisfy 2 constraints, one equality and one inequality. The V here corresponds to the points of the point game, the weights of the points, of the initial frame. And XG corresponds to the weight, the coordinate of the initial frame, the points in the initial frame. XH similarly corresponds to the coordinates of the final points, and W corresponds to the weights of the final point. Okay, so that is the situation. So, okay, I'm sorry. I should mention here that. I'm sorry, I'm just messing up the slides a little. Okay, so what we want to do is, if we can find such a unitary U for every step of the point game, then we can essentially construct the required protocol. And this is exactly what we do for Moshon's point game. And the unitary looks something like this. I flash it in front of you just to show you that it's compact enough to fit in the slides. It's not overly complicated. Given the background of the problem, this is a good thing. But I can give you some intuition about it. So imagine you have some points PG, endpoints, which you're moving to another set of endpoints. Then the unitary that does the following. It sends V to W, which is the initial weights to final weights. Then it sends the product of the coordinates with the weights to the corresponding product in the final frame. And of course, removing the component along the previous vector. And this procedure is repeated with higher powers of the coordinates, the matrices XG and XH. And that's essentially it. It turns out that this construction solves the problem that we need. I thank you for your attention. And if you're interested, I invite you to look at the article and also consider looking at the longer version of the talk. Thank you.
Thanks, Atul.
Yeah, thank you very much to all speakers. And I'll hand the floor over to Or to head the Q&A session.
Yeah, we have time for a few questions. If someone in the participants would like, feel free to add a few questions. So Thomas Vidic had a question to Anne. Anne, is there a clear relation to other single-use quantum crypto primitives, such as quantum tokens by Ben David and myself, or one-shot signatures by Amos et al.? By clear relation, I mean some ordering between all these primitives in terms of which can be constructed from which.
That's an excellent question. Thanks, Thomas, for the question. In this case, I don't think we know the answer. It's a little bit different here because we're talking about, I would say, returning information and not using it at all versus decrypting and reading the information. So I don't see directly the link because there's nothing that you can kind of use, and it's more about that you can use once. It's more about returning or reading. But I think this is a good point. There's a lot to be done in understanding how these primitives relate to each other, and is there a basic primitive that could kind of link all of these together.
Okay, thanks. Thomas had another question to Atul. Either still a question of efficiency around complexity of this protocol?
Yes, so there was a recent result by Miller. First of all, thank you, Thomas, for the question. Yeah, so there was a recent result by Miller. I think it's this year in Stock. I think that was published, and it basically addresses this to a certain extent. It shows a lower bound on the number of rounds, and it seems to scale exponentially or doubly exponentially. I may be slightly wrong, but it's certainly inefficient. So it was shown that you cannot possibly do coin flipping efficiently. However, this was in the asymptotic regime. So maybe one can actually do coin flipping with epsilon, say 0.1 or 0.01 or something in a reasonable number of rounds. And that might be okay. Although I would be surprised if that happens to be the case, but it's open indeed. Thanks. I hope I answered the question.
Yeah, I can talk, right? Yeah. No, my question was just whether your protocol matches this lower bound. So
no, not at all. Not at all. No.
So
There's a big gap. Yeah, it's much worse. Yeah.
Okay, thanks.
Yes. Thanks for the clarification.
We have another question to Anne by Ernest Tan. What are the main obstructions, if any, to extending the result to a composable definition? Since the protocol allows for the leftover hashing lemma to be applied, it would seem that it should be possible to certify epsilon indistinguishability from the ideal output.
Yeah, I agree. Our work here was focused on formalizing and achieving the first scheme to do this, but I actually think that our proof technique is amenable to composable definition because we could actually build a simulator out of it. So the only obstacle is to sit down and write this down.
Okay.
Thank you.
Thanks. Atul, would you like to ask the next question to Anne?
I think that's another Atul. I think there are two people with the same name.
Sorry.
That's not me.
Sorry.
Sorry.
So I don't know who that is, but there's another question by someone named Atul. Is it related to quantum bit escrow or cheat-sensitive bit commitment protocol?
Not that I know of.
I
don't know if someone wants to expand.
Yeah.
Okay, can I ask directly or?
Oh, sure. Yeah. Go ahead.
Sorry. So in quantum bit escrow, there is like two conditions. One is binding and one is sealing, and they only achieve either one of them. So I was just thinking if this is related to it, but I mean, it's fine. I can maybe ask you offline.
Sure, I'd be happy to discuss. This, it's surprising that we can achieve this. It just it's super sneaky to just go around all the impossibility results. It's not exactly bit commitment. It's not exactly this. It's not exactly that.
Yeah, that's true.
So, but yeah, this is always interesting to explore.
Okay, thanks a lot.
We do have some time to a few more questions. Maybe I could ask Atul. So one way I always wondered whether this is possible to construct weak coin flipping protocols is to use cheat detection for weak coin flipping, right? You could have a cheat that if you discover a cheating in one of the rounds, you immediately reject everything and stop. Right, and the question is whether there are any approaches to achieve that. Since you seem to have studied it carefully, then maybe you have any ideas regarding that.
Okay, so if I understand correctly, the formalisms that I've seen so far, basically motions and all of these, it seems that one can usually postpone first I should say that the cheat detection step is inbuilt into the formalism. So there's always this cheat detection step that happens. And when they try to generalize it, usually what they say is that, okay, you can postpone the cheat detection. So you can, even though you've detected it, you can somehow pretend that it's okay and you keep playing it, and in the end you say that, no, you were cheating, and so therefore I will not accept that you have won, something like this. So this is sort of inbuilt. I maybe have misunderstood your question. Maybe
sorry, maybe I could clarify. Suppose you had a protocol with some fixed epsilon, like with fixed bias, say 1/10, like a simple protocol.
Right.
Then you could run it in like 10 or n times, in say in parallel or in sequence. It doesn't really matter. And if you detected the cheating in any of them, you would reject, right? And then you would maybe maybe you would do a majority vote on the ones that, if the other person didn't try to cheat, you would simply do a majority vote. And that seems like the intuition seems to be that this should work, and I've never understood what were the reasons why it does not.
So usually I think the problem is that in weak coin flipping, we assume that there are two assumptions. At first, we assume that one player wants a heads and the other wants a tails.
Sure.
And when you have a string like this, so you're sort of doing like a string flip and then you're doing a majority vote. So there are two things. One is that the security proof is for just one round, assuming this is true. When you have a larger string, the strategy may be different. So a player may want to let you win a few times without actually biasing it and so on. So when you do the full analysis, it kind of turns back into the original problem, because you actually have to account for all quantum effects and so on. And then, so it's kind of general enough. I think maybe that, I don't know if that answers your question. We can discuss afterwards if you're, if you're interested. Yeah, I'm sorry.
Okay, thanks everyone.